Welcome to the Connectivity Rules tutorial. The human brain is a very complex system with trillions of connections that are organized in a highly sophisticated manner, allowing for the seamless integration of sensory information, the coordination of motor functions, and the emergence of consciousness and cognitive abilities. This intricate network, characterized by its vast number of neurons and synapses, forms the basis of our thoughts, emotions, memories, and behaviors. These connections are not static, but are constantly being reconfigured through experiences and learning, demonstrating the brain's remarkable plasticity. The organization of these connections into functional networks supports complex processes such as language, decision-making, and creativity, making the human brain one of the most complex structures known in this universe. In this tutorial, you will learn about connectivity rules and how they enable you to build the intricate brain networks. Network formation in the brain is a dynamic and complex process. Starting from developmental wiring, where neurons extend axons to target areas, guided by genetic and environmental cues. This evolves into synaptogenesis, where neurons form synapses influenced by activity and experience, leading to the refinement of connections through mechanisms like synaptic pruning and plasticity. Before delving into the connectivity rules, it's essential to understand that the XYZ coordinates always start at the 0, 0, 0 position. Connectivity rules define how neurons from one cortical area find its destination. In FEAGI, we support two connectivity rule types, vectors and patterns. Vector rules use magnitude and direction to define how neurons from source and destination connect. In this example, a vector of 0, 0, 0 indicates a direct translation. If you were to increase the x-coordinate of the vector by 1, there will be a translation of 1 to the right. If you were to increase the x-coordinate of the vector by 2, there will be a translation of 2 to the right. This also applies to the y and z coordinates as well. For example, increasing the y will result in a shift upwards. For the z coordinate, if you increase the z, it will result in a shift forwards. In the brain visualizer, select a cortical area, then choose Quick Connect to connect that cortical area to another cortical area using a vector connectivity rule. In this example, the vector definition is 1, 0, 0, so constant activation will result in a never-ending loop of the activation moving 1 to the right. 0, 1, 0 makes the activation move up 1, 0, 0, 1 makes the activation go forward 1, 1, 1, 1 makes the activation move diagonally. Pattern rules are more versatile and leverage wildcards to define how source neurons reach their destinations. Patterns can also be used to connect neurons with a specific coordinate to a neuron with another distinct coordinate in a 3D space. An asterisk in the coordinate indicates that all connections will follow the corresponding translation, like 0, 0, 0 to 0 asterisk asterisk, resulting in activating the entire row in the 0 coordinate. This can also apply to y and z coordinates, like 0, 0, 0 to asterisk 0 asterisk, resulting in the activation of every block in the first row. Likewise, 0, 0, 0 to asterisk asterisk 0 activates the entire plane in the 0 position. Increase the z-coordinate to activate another plane. In the brain visualizer, select a cortical area, choose Quick Connect to connect that cortical area to another cortical area using a pattern connectivity rule. In this example, the vector definition is the pattern rule from the source 0, 0, 0 to 1 asterisk asterisk, so the column in the 1 coordinate will activate. Asterisk 1 asterisk activates the entire row. Asterisk asterisk 1 activates the entire plane. Function rules are not editable through the user interface and offer a powerful method to define complex connectivity rules that can connect a source cortical area to its destination based on a set of criteria. The most versatile example of a function type rule is called the projector, which is capable of projecting neurons evenly from one cortical area to another. Please refer to FEAGI open source documentation to learn about function type connectivity rules and how to create one. The projector is a very versatile and simple method to connect two cortical areas together. It works in X, Y, and Z dimensions, and it projects neuronal activities evenly from the source cortical area neuron blocks to the destination cortical area blocks evenly, regardless of their shape or size. It can be used to condense information from a higher level dimension to a lower level dimension, such as condensing data from a 3D cortical area to a 2D or from a 2D to a 1D. It can also be used to enlarge or decrease the size of a cortical area to make it match a desirable size for further processing. In this experiment, the central vision is the source, which is connected to the various size destination cortical areas. The 16 by 16 square gives a lower pixel version of the 64 by 64 cortical area. The 64:1 activates the length of the vision, so as someone walks by, you can see the cortical area activate from one side to the other. The 1:64 activates the height of the vision, so as someone raises their hand, you can see the cortical area activate from top to bottom and vice versa.